author of the latest Can You Believe It article on the nanoscience revolution is Dr. David Wang, and he will be presenting our next demonstration to you.
White light from the sun or from a light bulb actually consists of a spectrum of many different colours. So you can see these colours, for example, in a rainbow, which forms when sunlight passes through water droplets in the atmosphere. So the path taken by the light through the water droplets is different for the different colours. So the different colours get spread out to form the rainbow. The path taken by a sunbeam can also be changed when it interacts with molecules and small particles in the Earth's atmosphere. In particular, these molecules and particles can scatter light in all directions. And it turns out that different colours of light are scattered to different extents. So blue light is scattered more than red light. And so scattering can separate out the colours, the different colours of sunlight when they interact with molecules in the atmosphere. I'm going to illustrate this scattering effect using a chemical reaction that produces tiny particles that scatter light, just like the tiny particles in the Earth's atmosphere. So here we have a beaker containing hydrochloric acid, which is a clear, colourless solution. The beaker is sitting on top of a projector which shines light through the solution and onto the screen behind me. As you can see, because the solution is clear and colourless, all of the light passes through, and so the image projected on the screen is white. So what we're going to do is mix in another clear, colourless solution, a chemical called sodium thiosulfate. So when sodium thiosulfate reacts with hydrochloric acid, it produces tiny particles of sulfur. And these tiny particles of sulfur scatter light, and in particular, they scatter more blue light than red light. So Graham is now going to mix the sodium thiosulfate into the hydrochloric acid. I want you to pay attention to the colour of the solution and the colour of the spot on the screen. So as the reaction takes place, more and more sulfur particles are produced. These sulfur particles scatter blue light out of the direct light beam. As a result, what's left in the direct light beam is mostly red light. So as you'll see the reaction progressing, you should see the solution start to glow blue and go cloudy because the sulfur particles are being formed. And you should see that the image on the screen changes from white to yellow to red as more and more blue light is scattered out of the solution, leaving just the red light in the direct light beam. So the same scattering effect explains why the daytime sky is blue and why the setting sun is red. So during the day, if you look directly at the sun, some but not all of the blue light in the light beam from the sun is scattered out of the direct sunbeam, and so as a result the sun looks yellow if you look directly at it during the day. If you look away from the sun at another part of the sky, what you see is the scattered blue light, and that's why the daytime sky is blue. Now at sunset, when the sun is low on the horizon, most of the light that you see is from the direct sunbeam. And because the light has to pass through a lot more atmosphere to get to you than it does when the sun is high in the sky, pretty much all of the blue light gets scattered out before it reaches you. So all that you see is the unscattered red light from the direct sunbeam. And that explains why the daytime sky is blue and why the setting sun is red. Thank you.